big list of co-authors up at the top. We did this program. Right? So myself, Gabriel Ferreira, Daniel Zacharias, Danny Natter, Lawrence Kellen, Dr. Steve Everman, Randy Davis, and Michael Alexander, Michael Brown, and Jeff Self. We did this as a class project. Yeah, and I'll talk about that. Obviously the title for our program is a plan for the conversion of stormwater to groundwater recharge on Utah Valley University main campus in Orem, Utah. So we did this in conjunction with the EPA Campus Rainforest Challenge. The EPA invited campuses across the country to develop green and economic infrastructures to manage their stormwater on campus and on site. So we decided that we'd throw our hat into that game, in that ring, and we organized this team and we started. It was a really good opportunity. We got to work with a bunch of students and faculty on campus, and we were really grateful for the facilities who were so open and willing to help us out with data and maps, and as well as Orem City, where UVU is. The Orem City stormwater team was really great to help us out. So these are our objectives. We wanted to determine on average what percentage of annual stormwater would be developed and captured on campus, as well as how much water would be captured in a 100-year, 24-hour storm event, and how much of that water we could contain on campus and use to recharge groundwater through a series of French drains, I guess. A little bit of background information about UVU. In 2011, UVU became the largest academic campus in Utah, which we had 33,000 students on campus enrolled that semester, or that year, but we only have 211 acres to work with. So the ratio of land to students is really small, and it means that the majority of UVU's campus is not a gigantic lake, but parking lots and sidewalks and buildings. And so we definitely had to pay attention to that. As we were designing our French drains, we couldn't tear up the parking lot. It just didn't make sense. The school would never go for it. So that was a huge concern of ours, was being able to put French drains into green space. Another problem with UVU is its proximity to Utah Lake, which you can see here. UVU is here in green, and the wonderful Utah Lake is only a mile and a half away. And as often do college students drive poor running cars that drip differential fuel fluid and oils onto the parking lots, and quickly all that wonderful hydrocarbons is moved off of UVU's campus as a storm happens and is transported to Orem's stormwater system, and eventually it makes its way to Utah Lake. And it's actually not a very long residence time. We didn't take time to figure out how long it took to get to the lake, but it was quite short. So we were definitely wanting to capture as much stormwater as possible. So in this project, we had a couple questions. One, which was hugely important, was how was the campus developed or divided into watersheds? It was too big of a problem to tackle with one giant watershed. It just didn't make sense. So we needed to go out and actually find that out. Another was how much water would we get in both the 100-year storms and in the annual precipitation for each watershed. So we knew how big our French drains needed to be and where we needed to put them. And that's kind of the next thing is, what would the location be and the dimensions of those. Also, further down the line, we'll talk about a detention pond that's already on campus where all of the stormwater from one watershed is pushed to this detention pond, and then later it's pumped out into the city's stormwater system. And we were hoping that just by shutting off the pump, we could use that as a French drain in and of itself. And so we investigated that. UVU's broken up into 61 watersheds. Dan Zacharias went around on a Segway with a ground level and ground truthed all of our watersheds. And we realized we had 61. 29 of the watersheds, which are in green, are self-contained watersheds, which means they don't export any groundwater. Some of them have little black grass swells or a little indentation in the grass, or also some of them had French drains. Down here on campus there were French drains that had already been built, but because of the high construction on campus, when we went and looked at them, they were all full of sediment and construction fill. So very little maintenance would be needed to be able to bring those French drains back into operation. We paid attention to the not self-contained, the watersheds that export stormwater, and those are delineated in blue. And there were 33 watersheds that export stormwater, which took up about 78% of UVU's total area. And this right here is our little detention pond, which drains watershed number 3, which is pretty much just this road. It's called Campus Drive, that you can see here. So according to NOAA, we found out how much stormwater UV or Orem would receive in a 100-year storm event, and also the average annual amount of rainwater we would have. So in a 100-year storm, like it says, we'd have about 2.3 inches of rain in that 100-year storm. And on average, throughout the year, we have about 13 inches of rain. Utahns have a hard time remembering that we live in a desert. This definitely shows that. In order to be able to decide how big our French drains needed to be, we needed to understand the hydraulic conductivity of the soil around UVU. So we went to the NRCS web soil survey, and we realized that UVU sits on top of 4 different soil or hydrologic soil groups. And they're outlined here in different colors. Now, because of all the construction on UVU, we were worried the construction fill would change the hydraulic conductivities that were recorded through the NRCS. We had spoken with facilities, and they had told us that that amount of construction fill, the depth, was negligible, but we wanted to make sure and calibrate our equations. So we went to our detention pond and used a well per meander in 8 locations to test the hydraulic conductivity in that area. And after we got our results back, 7 of the 8 test locations were dead on with the NRCS soil data. So we realized we could apply that across campus. The construction code really wasn't playing that huge of a role, and we were able to use the hydraulic conductivities and the rest of the data that NRCS had published on them. This is a map of the detention pond. I think we should have the north arrow here somewhere. This is kind of north, flooding this way, and the watershed drains coming down from here. These are the equations we use to calculate the volume of water we would have. So the coefficients are in, they're right there, you can see them. VR is our runoff in inches, P is the amount of precipitation in inches, and the IA is the initial abstraction, like surface storage. Concrete and asphalt has little cracks and bumps that the water gets caught in. So we had to pay attention to that, negligible amounts of rainwater wouldn't necessarily generate runoff. And the S is delineated as such, where our curve number depends on the land use and the hydraulic soil groups, which we also took from the NRCS soil survey. So as we took all of our data with the 100-year, how much rain we would have per watershed in the 100-year storm event, as well as annually, we knew how much water we were dealing with per watershed. And so it was time to start designing French drains. We made several assumptions when designing these French drains. As follows, it was just easier to work with rectangular French drains. It just made sense. Why would you have a circular French drain? But we also assumed that there would be a constant flow in, and also as it was flowing in, water would be leaving from the sides and bottom of that French drain. So we needed to add that into our calculation. We set the depth of our French drains at the water table according to the NRCS soil survey. Because we're so close to Utah Lake, the water table is like 6 feet. It's really, really shallow right there. And so we just, depending on the area where that soil group was at, we just used that as the depth of our water table, and we played, of our French drain, and we played with the width and length measurements to be able to get the proper size. And again, we were really conscientious about the French drains not interfering with any existing infrastructure. That was a big deal. So after everything was said and done, we were able to propose 9 French drains. And we have those French drains in kind of a lovely lavender color. Now all of our French drains minus 1 were able to capture and process the entire volume of stormwater that that watershed would see in a 100-year storm. -1, and it's this little dude right here. That little watershed there's a lot of building, a lot of space, and there's just a little bit of green space. And so the French drain that we proposed would be able to process a little bit, but not all of it. Unfortunately, we weren't able to propose French drains for the entire school. Again, because there's gigantic parking lots and tracks and ponds and different things. But we felt pretty good about the 9 French drains. So kind of our conclusions. Right now, as of today, main campus exports about a half acre for stormwater annually, and it would export about 23 acre-feet of stormwater after the 100-year storm. The self-contained watersheds right now, they capture and process 0.03 acre-feet annually, and like I said, it's 2.8-ish acre-feet after a 100-year storm. Now, after constructing our 9 French drains, we'd be able to contain 0.14 acre-feet, about 30% of the export after the 100-year storm, annually. And you can see the 28% of our current export for the 100-year storm. So it wasn't, we weren't able to retain 100% of our stormwater runoff, but we felt it was pretty good without having to destroy any existing infrastructure. It was cheap for the school. It would be cheap for the school to do, relatively easy, and we'd be able to limit, create less stormwater runoff. And I think that's it. Are there any questions?
Thank you, David. Well, we have as much time as we want.
Yeah, that was like 11 minutes last time.
No, I mean, we can go on forever.
Oh, yeah, all right.
There's not a talk coming after yours.
Moving on.
So does your university have water rights to all do you guys have the water rights to the property there? Nobody's going to be
As far as for stormwater,
Yeah.
we didn't really look into that.
Okay. I was wondering if somebody maybe
Wanted that stormwater?
Yeah. Well, I know some places they don't capture stormwater, it's capturing some of the recharge.
Yeah, yeah.
Like,
Okay.
I'm from Michigan, so I don't understand all the water rights, but
Sure.
I was wondering if maybe that was common.
Yeah, that's a really good question. We didn't even look at that. When we met with Orem City, with their stormwater folks, when we proposed the French drains, they were like, whatever you want. I mean, it wasn't that easy, but that issue never came up. But that's something you have to look at.
Can I just respond? We didn't actually look into that, like Dylan said, that there isn't any downstream use of it.
Okay.
All the stormwater just goes directly, eventually it's a pipe that goes into Utah Lake.
Okay.
That's not doing anybody any good.
We have one here in the back.
Going along with your green infrastructure, do you treating in the stormwater with vegetation or green techniques?
Yeah, that's a huge thing. We started the project that way, looking to build, what do we call them, wetlands, or different things that way. And as we started doing the math on how much stormwater we had, there just wasn't the space on campus to create a giant wetland. Actually, if I went back a couple slides, we did have a wetland on campus, but it was kind of an artificial wetland. But the higher powers decided they needed a parking lot part of the wetland. So it was converted to a pavement wetland.
One more?
Yeah, we had one back here.
Can you describe basically what a French drain is?
Oh, that's a great question. I'm sorry. So a French drain is a hole in the ground where all the water will drain to that hole, and it can either be a gravel-lined pit or a pit full of gravel, where the water is able just to enter that pit full of gravel and just hang out as it returns back to the soil as groundwater